To finish off section 1.1, we look at this last example about California condors and trying to make a model of its population. And the only information in the book that we're told is that it started off at a population of about 50 condors in 1968, and it decreased down to 25 in 1978. So this is a decreasing population. Now we're going to be assuming this is a density-independent model again, so regardless of the size of the population, its percentage change is going to be a constant value. But we now know that that value has to be a negative number because it's decreasing, going downwards. Well, again, we start with a flow diagram. Let's assume that we have some circle that represents the population, and we'll say it's P of t at any given time in there that we're trying to find. And as mentioned in the previous video, an outgoing arrow is one that represents a decreasing population because it's going away from the population. The problem is we don't know what R is. We don't know what the growth rate or decrease rate in this case is. So it is a question mark, but at least we can write something to represent it by. So we'll just say it's R times P of t minus 1. And this gives us at least a beginning portion of what we could write for the actual discrete dynamical system equation model that we're going to form. So after we clean that up, we see it looks very similar to our previous model that we formed with a flow diagram, but just the difference in direction of that arrow. But our formula will start forming out the same. One side is P of t, the formula that we're trying to solve for. The right-hand side, well, it always starts with the previous year's population, so P of t minus 1. And, well, as we said, outgoing arrows are subtraction, so that means we're going to be subtracting R times P of t minus 1. And that's all the information the flow diagram gave us, so that's what we get. So we have our formula, but it's still that growth or decrease rate in this case that is of question. We don't know what the value is, but we do have some values of 50 and 25 for years to go by. Notice, similar to our model that we formed before, we need a base year to start from. So in this case, t equals 0 is going to be 1968. So t equals 10 will be the year 1978. So we know that P of 0 is 50, and P of 10 is 25. So let's go to Excel and see if we can work with this. Maybe we can figure out what the decrease rate is with the same principles of how we made our last Excel spreadsheet. So here I've set up our Excel spreadsheet in a very similar way that we did for the grizzly bear population. I've written our function up here, the only difference being now there's subtraction going on with some rate. And really, I should change this to an R value because we don't know what that value is yet. And the decrease rate is just some fixed parameter that we're going to put in this box for now, and we'll play around with that value. Maybe we can guess and check what it would be and see what Excel tells us. And I've labeled our years as 1968 through 1978. We're assuming there's an annual decrease, so that's what this decrease rate will apply to. And the beginning at year 0 is 50. So, like we did before, let's make the formula for the next year. So we always start with equals, and we take the previous year, and now subtract the decrease rate times the previous year. And, just like before, let's click on the cell reference to G2, and make sure that's an absolute cell reference. We don't want the decrease rate changing with the row reference changes that we're going to be filling out this formula with. And when I hit enter, I'll see a value of what the 1969 population is. But remember, from actual data, we know that in 1978, the population will have decreased down to 25. So if I click and drag this, remember the fill handle in the lower right-hand corner, and let go, at 1968, we can tell whether our model is accurate enough if that value in 1978 is 25. Well, notice it only decreased down to 45, so it seems like this decrease rate is incorrect. But, again, the niceness of Excel, we could just play around with that value of decrease rate and see what eventually gives us our answer. So maybe if I went up to 3%, And that puts us in the correct direction. I can see now at 1978, the population is down to 36. So certainly it's decreasing from what we had of 45 before, but we still need to make a larger decrease rate. So if I keep inching towards it, 4% is not enough. 5% is not enough. 6% is not enough. And 7% is too much. So our decrease rate must be somewhere between 6 and 7%. And after we play around with it for a while, the value that the book attains is 6.6% about. We could go to more accuracy and using more decimals, but this seems roughly close enough to what we're shooting for. And this allows us to use Excel in a quick, efficient manner to make these guesses and checks without having to make these calculations over and over ourselves. So this leads into your first assignment that you will see on Canvas of exercises from the book on page 19 of the various different questions and models that we'll try to answer and make. So you should be able to complete those exercises using the techniques of Excel we've learned here and in the previous video.